All right, we're starting off thermochemistry with endothermic and exothermic processes. So when something is endothermic, we often think of that there is a net gain to the system. So that means the heat goes into the system and leaves the surroundings. So a decrease in heat to the surroundings, increase to the system. Exothermic, we often think of as being warm because we are in the surroundings all the time. We're never part of the system. At least we hope not. Otherwise, we've done our lab wrong. So this is reaction flows out of the system as the reaction proceeds. So the system will decrease in heat while the surroundings will increase in heat. So you might say system and surroundings. What does that really mean? So the system is usually the chemical processes we're thinking about and looking at. Surroundings is everything else in the entirety of the universe, but we're usually thinking about the near surroundings. And so all the things we study with energy is the system and the surroundings. So if something is endothermic, like our beaker of our chemical reaction, the surroundings lose energy, and since we're in the surroundings, it's going to feel cooler to us. This is a change in enthalpy that's positive. If it's exothermic, the change in enthalpy is negative, the surroundings get warmer, the system decreases in energy. Most reactions in the universe are exothermic, not endothermic. So endothermic reactions feel cold to us and would look like this upon a reaction coordinate. So you've got the energy of the reactants are at a lower energy than the energy of the products. Activation energy is this energy that's required in order to get us to the energy of the products, and the change in enthalpy is the difference from the products and reactants. You'll have to understand that qualitatively and quantitatively in this energy diagram and across all thermodynamics. Of course, exothermic, you start off with more energy than what you end up with. As you can see, the activation energy is always higher than the energy of reactants, which is why energy needs to be put into the system in order for it to react overall. It's not going to react all on its own. And the difference between energy of products you see is a decrease in enthalpy as the reaction proceeds. Now, in chemical reactions, again, trying to show you some more illustrations of what this looks like. You've got this gigantic compound reacting with oxygen to produce carbon dioxide and water, an easy combustion reaction. You always need to add energy to break the bonds that are already there, and then energy is always released in bond making. So it's always going to be released, and we need to see what is the sum of each of these. When it's exothermic, we're going to have a decrease from what we added to what was released. Again, exothermic being negative, as the delta H will be negative. Now, this is also true with phase changes. I often don't think of them myself as endothermic or exothermic unless I'm stressed to. But when we think of certain types of phase changes, some always are going to be exothermic and some are going to be endothermic. So in order to go from solid, liquid to gas, you're going to be talking about adding energy. So you add energy into the system, meaning it's going to be endothermic. Things like deposition, freezing, and condensation, we're releasing energy to the surroundings. And so when that occurs, it's going to be into the surroundings, going to be getting cooler. One of the things that I always think is kind of interesting is the fact that when you have something like rain, a gas becoming liquid, clouds, and it's water vapor becoming liquid, it's actually releasing energy to the surroundings. This is one reason why when you have often rain, it's not so cold as when you have just no rain, because it's releasing energy to the surroundings. Now, what here is called a heating curve that we have here. We have many ideas of enthalpy of fusion and enthalpy of vaporization. So in order to fuse something, or I should say melt something, they call it fusion, but it can be either way. It takes the same amount of energy to melt something as it does to freeze it and release it to the surroundings. Likewise, when we vaporize something, we have to put in a whole bunch of energy in order to make it a gas, and that same amount of energy needs to be released in order for it to become a liquid again. So we can see that there's a lot of different phase changes here, and that as we go up, all of this would be endothermic, because it's taking in energy. And if we were to go reverse down this heating curve, it would be exothermic because it'd be releasing energy to the surroundings. That's often not what we think of when we think of ice forming, going from a liquid to solid. We have to think, oh, it's getting colder. It's getting colder, so the surroundings has to get warmer. This is why your fridge and freezer needs to pump out heat in order to freeze or chill things. Often it's hard to wrap our heads around, but if you just think about going from a liquid to a solid, you have to release energy. And where does it go? It goes to the surroundings, and we're in the surroundings, so that's what we feel. Now, the last example of exothermic and endothermic is involving making solutions. When we dissolve things, there will always be either an absorption of energy or a release of energy. We often use tiny amounts. We often don't think about it. There are some examples we could show you in class that would be pretty dramatic, and some of them might be minor to where you might be fooled into thinking, it went up a degree. That's just getting used to the room temperature. So I'd like to think of you thinking about this and the idea you have a solute, it's solid. And if we broke all of the bonds present, it'd be like making a solute that's gas. All of the particles are far apart from each other. If we also think of the solvent, which is a liquid, it has interactions amongst the liquid molecules, make it also a gas. So if we just took all the energy that makes them gaseous, what would that be like? Then if we added the solute and solvent and made it aqueous, so we go from being separated to now being mixing and being in contact with each other, it looks a lot like this. So the idea is that you have so much energy to break the intramolecular forces holding it together because it would be bonded, right? Or I guess it could be also, if it was a covalent compound, it could be intra or intermolecular forces. Solvent breaks apart the intermolecular forces holding it together like water. So all of this will require energy. Now when they come back together, it's going to release energy. And then we see, in this case, the heat of solution is a positive value. So if that is a positive value, that means the surroundings are going to get cooler, okay? Because energy went into the solution. Where does it come from? It comes from the surroundings. So that means a decrease in energy, which is going to make us feel cooler. Exothermic example, same idea. Breaking these into its gaseous form takes energy, and then putting them back together is going to decrease the energy. Again, when we think of the solute, often we're thinking of ionic compounds, but even covalent compounds like sugar, dextrose, any of those kind of other sugars and things do have intermolecular forces. So you can kind of replace this intermolecular forces. And again, the solute's doing the same. This is a release in energy. That means the heat of solution is negative. That means it's releasing energy to the surroundings, so it's going to feel hot to us. It's going to feel hot. So there's some great examples of these across. And so keeping in mind that when we think of something as becoming an aqueous solution, there's always energy taking in and always energy being given off. And based upon the sum of those, if we have more released than taken in, it's going to be exothermic. The opposite will be endothermic. All right, so hope this goes over. We're looking at exothermic, endothermic. This will be across the board, something that's always present. So get used to thinking about which way is which based upon what is going into the system or leaving the system and how the surroundings are feeling to us. Come in with your questions. Talk to you later. Bye-bye.